Thank you. When I was asked to give a talk, I picked up this title because this is the first paper I wrote at IS when I was a postdoc, like almost 27 years ago. In that time, I tried to develop a height pairing of and the curves to give a convenient computation of narrow heights. And at that time, I was thinking about the Bogomolov conjecture, and it's really used, prove a Bogomolov conjecture. Then later on, I work on the Grozagiev formula. Fortunately, this also be used in the Grozagiev formula. But recently, there's a lot of activity trying to do Grozagiev formula for high dimensional variety. So I'm thinking there should have some foundation for the heights. So before I do everything, I just review what's going on for the curves. So we start with the case and number field. So x of k, the proper curve, proper smooth. Then we have the divisor or Picard group, whatever, it's a Picard group of x. The inside have a Picard group of degree 0. And here, this is basically this is equal to Jacobian of x and the k points. So here we have a so-called narrow height pairing. And which is, if we tensor with Q, this in fact is a positive definite. So the first question, how do I extend such a pairing? How do I compute it? If you think how to compute it, but degree 0 is always a problem because it's always difference of 2 points. It's more convenient if you compute a height pairing for 1 point. Right? So the first question, can you extend this pairing to a whole Picard of x instead of this thing? Of course, you can have very much a stupid way to do that. For example, if a fixed error is a line bundle, degree of error bigger than 0, then you have a direct sum of Q, your Q times error, the class of error, times Picard 0 of x. You can put a number here, we are done. But that's a pretty stupid thing to do, right? So this is meaningless. So we want to do a more fancy way. So one more fancy way to do that, you pick up a regular model. So the regular model doesn't require minimal, just some model. And then you complete some way. You put some Kimden points. So then you have typically in number theory, this should be completed by infinite place. So you have for each v divided infinity, you have this Riemann surface xv of c. So in any case, then your error will be completed by ample line bundle. Then you put a metric for each v divided infinity. So you want this metric, you want this one to be not only ample, you want to be arithmetic ample. So this means that is a typical way, means that vertically it is ample, so error is ample. This one is a metric there, which has a positive curvature everywhere, plus this metric has a line bound are going to define the heights. You want the heights to be positive at every point. So we're not going to define that. So you do this way. Once you do this way, you can do something very interesting. So then for example, for each place V, we can define a Green's function. G of V on xv of cv. So the cv is kv to a closure. And you define by following way. If v divide infinity, this is basically the one defined by our Kernel. So this you have dd bar. So this Green's function is a gv is a function and xv of cv cross xv of cv. Take the diagonal out with a logarithmic singularity and the diagonal. And if v divide infinity, you have equation dd bar pi I as a distribution of x and y. So let's write as x here equals, let me write down. Okay, let's write a delta Laplacian operate dd bar divided by pi I, then divide by C1 of L with this norm. For simplicity, let's assume that the degree of L equals 1. So this is Laplacian operate. Then you require the Laplacian operate of gv xy equals delta y of x minus 1. So that's the equation you're doing. So v not divide infinity, you can do similar thing. What we're going to do is that you have this g of v x and y. It will be this iv x and y. So this is the intersection of the closure x bar y bar, right? If you have two sections of your surface here, you have 2 point x and y here, then take closure, you get somewhere here. So this is the v here, you have intersection multiplicity. But this is not enough. Then you plus a jv of xy. This jv xy is a Green's function on the dual graph of x of this x of fv, residue field k of v. So once a dual graph, it becomes it's just like a manifold, like a topological space, piecewise smooth, with respect to a Laplacian operator equal to negative d square of dt square. But this is not self-adjoint. What we're going to do, you take 1/2 of this one, negative 1/2, then plus the adjointization. Adjoint of this operator. So once you're doing that, you get these two Green's function. One is at a finite place, one is infinite place with a finite place. Of course, you can use the Berkovich space language to do this thing, but anyway, that's a very initial way to do that. So once you do that, then the pairing we're going to choose is the following method. So what? T, you have doesn't matter if you have a graph. Any t, because your second derivative doesn't depend on the direction you choose, right? So you can choose any direction you want, right? Yeah, first derivative will be trouble. You should pick up any orientation. Okay, so this is for any. Of this of a dual graph, maybe give a name called gamma. So that's the theory. So I defined the height pairing. So the height pairing admissible height pairing will be defined by following method. So x and y, say it's a height pairing. So like Harris-Taylor, right? It's equal to summation v g of v x and y, of course for x not equal to y, of this epsilon v plus degree of error bar and an x bar, or plus degree of error bar and y bar. So this epsilon v, as usual, log normal v. So the log of cardinality k over v, and 1 or 2, this v is not divided infinity. The v is real. The v is a complex. Okay, so you get such a pairing, and you go back to check. This is a positive definite. This we extend their narrow height pairing. Right? It's a very nice one. So the theorem is, so this extended to a pairing on pick of x and the k bar, whatever, and which is a positive definite. And extending the narrow height pairing. Great. So this is really nice. Some things done, and I give you further relation with this lecture. Let's try to compute one of them. I mean, I could compute. So for one example, since this is a conference workshop, but locally symmetric space, I pick up one case. Say this v is in infinity. My xv of cv supposed to be upper plane modular a gamma. Right? For example, assume this is true. So this is upper plane. This is a gamma. Is x there free? Is a co-compact? The gamma is inside PSL2 or real number. Then your Green's function is in fact can be written down as limit s goes to 1 some other Green's function x and y, take the residue of s minus 1, something like that, and this is g of s. Y will be the summation negative 2. I'm not 100% sure of this thing. Of q of s of z minus w twice imaginary of z, imaginary w, the gamma w here, then plus 1 for gamma inside the gamma. So this is see that this is like a Poincare series, and this effect is a typical resolvent for the inverse of Laplacian operator. So the QS is x u is given by precise integration u plus square root u squared minus 1 hyperbolic cosine of t negative s dt. So in fact, this is a solution of second order equation with regular singularity at t equals 0 and 1. Okay, so and you probably can have similar formula for manifold curve, but I have not yet figured out how to compute it. I mean, Yesterday when I tried to do the lecture, trying to do this tonight, I could not. But it must be some similar formula. Okay, so this is the theory for curves. So now we want to do the general variety case. So what we're going to do is the same thing. So we have x over k is a projective variety, and we have so this is the arithmetic ample line bundle. We're not going to define that, but the similar thing. So one way you can do, I mean, this is I spent quite a lot of time to define this notion. It could be the limited situation, but the simplest case is that you have a model. Say this is a regular model, and this one, the error bar is similar. It's error plus symmetric. For simplicity, we also assume the C1 of this error at the generic point. So this is the dimension equals n equals 1, for example, just scaling. So this is just like it's a Q, right, coefficient. So this is the peak of, I mean, error is the peak of x tensor Q. So then we have similar problem we want to define. That's how we want to define a height pairing on the Char group of x here. Right. So that's something you want to do. You want this one to be positive definite. Right, and there doesn't depend on anything. Suppose this is only data, you're supposed to depend. But it doesn't depend on the model you choose. Of course, I mean, if you're ample, you probably don't have many choices. This is something you want to do. The reason is, when you do intersection theory, you either to consider the integral model, blah, blah, blah. It's complicated. You want to have a theory only depends on one data. For Schumann variety, it's even more important because if your group fixes this data, you're going to fix everything, right? So you.
Why this is positive? It's supposed to be the same.
It's a positive definite. Yes. Now, Hodge index theorem. So in fact, what I'm doing is the Hodge index theorem has signature n and -1. My definition just switch the second one to positive. That's the only thing I'm doing. It's just I switch the sign. So for this theory, I really need to require, what I'm going to do is that I'm going to conditionally, I need to record the conjecture. This is a conjecture by Gillet-Soulé. On, I mean, called the conjecture, I think the arithmetic analog of standard conjecture. So this is something we can assume. So idea is that you have on this variety, you have these cycles of x here. So this arithmetic Chou cycle of codimension I. And then you have a pairing of x here times So I usually put a Q coefficient, for example. We're not going to define that, because define that thing is going to be complicated to real number. If I plus j equals m plus 1, then there's a C1 of L. Define a pairing. So define operate. Defines operate. Left type operate. So chi of x to chi plus 1 of x. So let's write this operate this way. So the conjecture, the formulate is the following method. The conjecture. So let I less equal than m plus 1 divided by 2. Then this L n minus 2I will have, so we have this operate I of x to ch m plus 1 minus I. But m plus 1 is always dimensional arithmetic variety of x. So let's put a q, and maybe I should even put a, I have some trouble to understand this coefficient I'm going to choose, q, or maybe, I don't know, it doesn't really matter, or real numbers. I may put real numbers. Yeah, I just don't want to do anything. So anything difference between, probably q is enough, right? So the conceit. So then the first thing is n minus 2I is bijective. The second thing is that if we took one more step, so if x is inside ch of I of x of q such that m plus 1 m plus 1 minus 2I, then plus 1, you take one more step of x equals 0, then negative 1 to the i's power to the intersection between this one and this one, L m plus 1 minus 2I, x and x is always positive. And if this one is not 0, so this is a very, very strong conjecture. Okay, so what's the good thing about this conjecture? Once of this conjecture, I can define so-called primitive class. So we can define the primitive class pi of x. So let's write a bar here to recall that we are doing matrix n. So this is called kernel of L m plus 1, m plus 2 minus 2I on this operator. Right? So the conjecture implies that this group is equal to the direct sum. Is a sum. It's basically a direct sum of L of m k equals 0 to m plus 1 over 2. So I minus k of p of k. Right? So we define we have this thing. And so because of this reason, so we can define what? Chow hat, yes. So we can define, now we define a height pairing. So we can define a height pairing by changing the Hardy pairing according to this formula. So I can define for x and y inside h I of x. So I can define the x and y, the Hardy pairing, to be by this formula. So if x equals to summation I minus k xk, y equals I minus k yk, I can simply define by most naive way to do that. Summation -1 to the kth power of xk yk. So this is the intersection pairing. So according to the conjecture, this should be positive definite. So this should be, so this pairing should be this. So this is a positive definite. Right? They define a pairing there. That's very interesting. Then what's left is not hard anymore, though. So what's left is the following. So we have this pairing of I of x of surjective morphism. So ch I of x, right? We have this surjective morphism. Well, you have positive definite pairing here. You have morphism there. Somehow also there's a conjecture said this should be finite dimensional. For example, this should be finite dimensional. So you have orthogonal complements. You can talk about it, right? So I can have orthogonal lifting. So what I really mean that I have these called vertical cycles. I can take the orthogonal complex of this in there, embedded there. So this define a Hardy pairing. On CHI. Oh, wow. Done. So if you assume the standard conjecture, you definitely have a Hardy pairing. So this is a pairing. If you check it, this is a pairing should generalize extending the pairing given by Bellings and Bloch. It's not difficult pairing on homological trivial cycles. And in the curves case, that's exactly what I do. So I define this way. The question is how do you compute this pairing? But forget about the proof of this conjecture. Well, so in one case, at least the conjecture in one case is proved. So the standard conjecture holds when I equals 1. So this is by many people's work. I mean, the beginning work is the Hurriel in the curves case, Hurriel Jack Faltons. Then the Moriwaki. So this is for curve. This is for algebraic case. For idyllic case, it's proved by Yuan and myself. So this is true. Once this is true, I should have a way to construct such a pairing. So I just construct this one for you. So let's construct. So now I want to construct pairing. I really want to construct for any m. So this is what let's going to do the following way. Let's write the theorem. For any line bound M inside a pick of X, there is a unique new unique arithmetic extension of, say, M bar. So this is basically a metric. The metric has a line bundle. If I write this way, equals this in. Up to pullback. I mean that if you have the x here, spec OK is pi pullback of a pick bar of OK, the degree equals 0. So if you have a divisor here, your degree 0 pullback, that I don't want to consider it. Just such that the following condition holds. The first condition is, so this error for HV, so this metric is harmonic with respect to C1 of L of V. I need to explain for V is Archimedean, there's nothing, no problem. For non-Archimedean, I explain what do you mean the harmonic. Second part is, of course, I have to say it's orthogonal. So this is C1 of C2, C1 of L bar of n equals 0. Well, this is not difficult. Just add some constant, make this 0. Right? So I need to explain this condition. So this condition involves some harmonic analysis. So if V is infinity, it simply means that C1 of L, the M here, is a harmonic form. With respect to this end, to the C1 of L, this stuff. So this is like a Kernel form there. But with not infinity, I don't have at least I don't know how to do harmonic analysis on this general situation. But this condition can be translated in a different language, which is observed by Calabi. Calabi say this is harmonic exactly means C1M of C1L to the m minus 1 power is a scale times C1L as a measure on XV. Maybe this time I try to write it down in the Berkovich space. And in Archimedean plate, these two conditions are equivalent. So you put a measure here. You can define this measure using intersection theory. Then this condition, the non-Archimedean place, can be translated by this condition. Okay, so this is in the line bundle case. Somehow we can solve the problem. So what I'm trying to say, for line bundle, you can define a heigh pairing. And this theorem gives you a unique way how to extend, how to give you any line bundle to get a metric there. Well, this is pretty much the only thing I know, because I really don't know how to do harmonic analysis for other current. For one form, I know how to do it. For other form, I don't know how to do it. So maybe the Hodgkin theorem maybe can give me some idea how to do this thing.
Did you finish this theorem?
Done.
Done?
Yeah.
Okay.
This is the one I just explained, this first condition. What's harmonic?
Saying now there exists a pairing with such and such.
Oh yeah, pairing. Yeah, pairing is M1, M2 equals a negative intersection numbers. Okay, So this will be positive definite and a Picard group. Okay, so this is my second part. So I propose a definition, but I really don't know how to prove anything other than line bundles. So, but again, so now the third part, so this is most related to the workshop because I want to say something about locally symmetric space. So to prove such a conjecture is impossible, to construct the pairing, you really needed to construct. So needed to construct Green's current. So we'll talk about Green's current. I came to place. So now I want to do a very simple thing. I have x over c is a complex, proper complex variety. And my omega is a Kernel form. For simplicity, I always assume omega n equals 1. So nth dimension of x. So then by Hodge theory, by Hodge theory we can construct. There is a green current. There's a current G x y and x cross x such that dd bar of pi I of g. So this d is on x cross x. It's not a one variable, two variable dd bar equals to delta diagonal current. So this current is a degree n minus 1, n minus 1 minus the harmonic form. So this is a harmonic form representing of the class of data inside the cohomology of n x cross x. So you have such a class. So the question is, how do I construct such a class? This is just existence theorem. And a funny thing, there's not so many references how to construct such a thing. For curves, the one I just did, that's a way of doing. For high dimension, it's pretty hard. So one thing I found out is very interesting thing is that there's a proposition. So actually this current can be written in terms of resolvent kernel for Laplacian square. So that's what I'm going to do right now. So what to do is the following thing. So I have to, this is a space of smooth forms. Smooth forms and x, right? And then this is the topological direct sum C of eigenforms. This is phi inside B. So this is phi is eigenform for the Laplacian operator d star plus d star of d. We also assume this is norm 1. That is also normal basis. This is also normal basis. B is orthonormal of eigenforms of pure degree. Okay, just everything the degree is the same. So I can define let it B star the non-holomorphic one, a non-harmonic one. So I just take harmonic one out. So I can write on one resolvent of R x and y equals summation of phi of x tensor phi of y bar over the lambda of phi square. Okay, so write one resolvent. So this is, it's off from diagonal. This is inside A of x cross x. So the one proposition is the following. So the green current there can be written down something like that. This one, the G xy 1/4 d star d bar star and another operate 1 tensor -1 of degree, because each phi you have a degree here, then times star operate times Rxy.
I'm confused what is wrong. This equation dv bar v equals something that will not give you v uniquely. So what more do you want?
Oh yeah, I want orthogonal to.
Do the v and v bar of anything?
Yes, you see this. Okay. This equation just implies that G is orthogonal to all harmonic forms.
Yes, but you have an ambiguity in d modified by d.
Image of D. Okay, so if I require G to be perpendicular all harmonic forms, this is unique. Okay, let's say the following. This one is the solution for this equation. Because for the integration of the thing, okay, I'm sorry, he asked me a question, reminding me why this thing has used for the pairing. So let me before I do that thing, I just show you. So once you have the green current, if you have the y z.
Where does delta squared and lambda squared come from?
What?
Why is there a square on the Laplacian and on the eigenvalue?
I saw write the propositions. It means they need a proof. So it's not a. so I just show you how to use what green current will be used for. If you have this x, the kernel is with support, then you can define a yz intersection number to be integration of x of gxy delta y delta z on x. Suppose the dimension y plus dimension of z is n-1. I forget the codimension, right? Usually. What? n-1. Otherwise, dimension, you are going to confuse it. So you can use that thing to define a pairing. It's just like a curved case. Now you define a pairing between two cycles instead of 2 points. Okay, so but this one is difficult to compute too. So what can you do? is probably you're trying to change it to the Rs xy to be phi and b, but this time you want a lambda phi plus s squared, phi of x, phi of y. And the relationship to this one, of course, is the Taylor expansion s equals 0. You take a residue out. But this one is more, it's more easier to manage, because this one is related to the green current. So if you write a phi of s equals summation phi of x phi y by over the lambda phi plus s. In this case, this is more manageable. So this r x and y is, of course, it's a convolution of this kernel twice, right? So it's a dz, right? You're going to get this stuff. So we're going to compute this in. Okay, so now finally, I move to locally symmetric space. So now finally, I ask x to be the G mark K or the gamma. The G is a semi-simple Lie group of real number. K is maximal compact. The gamma is discrete subgroup. We assume this is free, whatever. And then, as usual, we take the Gaussian decomposition. So then this operate is is simply let V to be the forms. So this one you can write down as isomorphic to all the functions. So f of maybe f here from G cross G to anamorphism of V, such that the following thing, where the usual thing happen. So this has action over the K, so given name called tau, such that f gamma 1 G 1 K1 gamma 2 G2 K2 equals, let me see, what's the equation? Tau K1 inverse composed of F G1 G2 composed tau of K2. Okay? On the other hand, you say this equation suggests the following. So if phi, if phi, so we're trying to, so this is a two variable kernel, so easily, because it doesn't depend on gamma 1, gamma 2. So one way to do that, so one way to construct such a, so if one way to construct such a section is to use the Poincare series. So this f of G1, G2 will be summation of phi G1 inverse gamma G2. But this phi right now is a function goes to anamorphism of V. Satisfy the usual translation. K1 GK2 equals K1 tau K1 compose phi G compose phi of K2. Right? And you want phi to be rapidly decay. But otherwise, this one does not convergent. So there. So the conjecturally want to say is the following. I mean, since I could not prove the general case, so there is a phi S inside this phi S. I don't know, I need to give a name for this thing. Maybe say this kind of thing, this kind of space. Let's give a name called, I don't know, I mean, so called C of G tau. But I need to take the E out because this we have a better singularity at E of C G. I'm not only taking, you really take a K cross K out of tau, because if E is better, the OK will be bad too. Such that, so the corner right on there, the phi of S is exactly equal summation of phi S x inverse gamma y. And the theorem I want to show, I don't know, let me write the theorem first. So the conjecture holds. If the rank, split rank of G equals 1. Well, then now I explain why I do this thing, because I don't know how to solve PDE. I don't only know how to solve ODE, right? So I give you some remark. So the remark is the phi S in the conjecture, maybe I don't know, use phi S is probably the better idea. I use QS like that. Satisfy an equation C of phi S, right? C plus S of phi S equals 0. Delta of E. So this is basic differential equation is satisfied. If we drop this condition, then the solution for this one is already given by Hirsch-Chandler, right? Without the singularity, delta E solution are given by given as the generalized spherical condition Eisenstein integral by so it's explicit integration. But the Eisenstein integral has a property that is nice at E, but actually increase at the boundary, like a polynomial increase. What I want is exactly opposite. I want exponential decay in the boundary, but singularity at infinite. So you can think about so in this way you can think about phi S is a secondary Eisenstein integral. So if we use the Gaussian decomposition, the G equals nk na of k, so maybe plus here, then phi s satisfy a equation Laplace, radical exponential plus some operator. So if I write down, that's just like usual, e to the lambda plus e to the negative lambda, e to the lambda minus e to the negative lambda, but lambda inside the positive thing, m lambda plus h of lambda plus operate. So this is operate inside anamorphism of anamorphism of M of V. The M is the centralizer of A in the Lie algebra. So this is the same differential equation as the Hersh-Chandler's spherical functions. And this differential equation has a singularity along the boundary of Y-chomp, and which I don't really know how to solve it. And if the split rank is one dimension, it's just usual ODE, then I know how to solve it. So that's basically why I know how to do the problem for split rank, but not for other case. But I believe that this should be true in the fourth journal. Okay, maybe I should stop here.